Hello everyone, I'm Ehsanul Kabir from Pennsylvania State University. In this video, I'll present our innovative framework, FLShield, which addresses the critical challenge of securing federated learning systems against poisoning attacks while maintaining data privacy and efficiency. This research work was jointly done by me, Jiu Sung, Mohammad Rafi Rashid, and Shagufta Mehnaz, all of whom are from Pennsylvania State University. Federated learning is transforming data analysis in safety-critical domains, but it faces significant security challenges. One such challenge is its vulnerabilities against poisoning attacks launched by some of its participants. First, a little background on federated learning. Federated learning is a decentralized learning process which spans across multiple iterations. In each iteration of federated learning, a central coordinating server sends a global model to the participating clients who train a local model on their private training data and sends their local model updates back to server, who then aggregates them to get the updated version of the global model. Some of the participants can have malicious intent and perform a wide variety of poisoning attacks. For example, malicious participants can mislabel all of their training data with the goal of reducing global model accuracy. We call that an untargeted poisoning attack. Alternatively, they can mislabel samples from a source class to a target class level and perform a targeted level flipping attack. They can also introduce backdoor samples in their training data and launch a backdoor attack. Additionally, they can craft their local model updates in a way that the global model is also impacted after aggregation and behaves in the attacker's desired way. This class of attack is called a model poisoning attack. All these attacks pose a significant threat to the integrity of the federated learning process, and therefore it is of paramount importance that we take defensive measures against them. There exist some defenses against different types of poisoning attacks, but they all suffer from some drawbacks. For example, some of them assume that the server has a set of clean data matching the distribution of clients' training data. However, it is an unrealistic assumption in many privacy-sensitive domains. Some of them assume that the malicious model updates are parametrically distant from their benign counterpart and launch clustering or anomaly detection algorithms to filter them out. For example, in the figure, delta 1 represents the distance between two benign models. Delta 2 and delta 3 represents the distance between the malicious model and each of the benign models. The distance is usually computed after flattening the model parameters into a one-dimensional vector. This assumption may not be true in scenarios where benign clients have high degrees of non-IID data. For example, if the benign client in the upper side and the malicious clients have similar data distribution and the benign clients have less overlap in their data distributions, it may be possible that delta 2 is less than delta 1. If that is true, the anomaly detection or clustering algorithm may fail to filter the malicious model update. To address the shortcomings of the existing defenses, we take a validation-based approach where the validation is done on the client side. Clients are the real owners of the data in FL, and that's why we believe this step is critically important in designing a defense. In FLShield, the server selects a subset of clients as validators who validate local models on local data to decide which of them are benign and which of them are malicious. However, the process of validation in FL comes with two challenges: validation subject dilemma and validation integrity dilemma. First, let's see what these dilemmas are. Since the validators are chosen from the set of participants, some of them can have malicious intents too. They can launch gradient inversion attack on the local models they are given to validate and uncover sensitive training data from the model. Therefore, it is unsafe to use local models as validation subjects. We refer to this challenge as validation subject dilemma. Similar to the way malicious clients send malicious model updates, malicious validators can report incorrect validation results. They may report that benign local models are malicious and malicious local models are benign. This thread poses a question, which is how can we filter these spurious validation reports? We call this the validation integrity dilemma. To solve the validation subject dilemma, we propose a new technique called representative models. What are representative models? Representative models are models crafted from the local models at each iteration for the purpose of validation. We designed two approaches of crafting representative models. One is bijective and the other is cluster based. In bijective representative model, one local model is selected as a base or mold, and contributions from the other models are added with respect to their similarity to the base local model. In the right side of the equation, the second term indicates the contribution from the base local model update, and the final term indicates the contribution from the other model updates, which we also refer to as sibling contribution. The parameter tau controls the amount of sibling contribution in the representative model. In the cluster-based version, all local models are initially clustered into one of n groups, where the value of m is determined dynamically to ensure that the model updates within the cluster are close to each other and model updates from different clusters have noticeably higher distance. After the groups are formed, a representative model update is computed by aggregating all local model updates of one of the m groups. We found that the use of representative model prevents the malicious validators from successfully launching gradient inversion attacks. To solve the integrity dilemma, we propose a new validation metric, LIPC, which is short for loss impact per class. LIPC is computed on a class-by-class basis to ensure that malicious models sent by clients launching targeted attacks can also be identified. The loss impact in LIPC refers to the difference in loss computed on the current global model and the representative model that is being validated. In our experiments, we found that LIPC remains consistent among the benign validators, which helps us filtering spurious validation reports. Now, I will briefly go through the design components of FLShield. In the first step, clients train local models, and then these local models are used to generate representative models. Then a set of willing clients are chosen as validators. The representative models are then sent to the validators. The current global model is also sent to the validators for their LIPC computation. The validators send validation reports, which are then filtered using an anomaly detection algorithm. Then we rank each representative models based on the validation reports and keep the top 50% corresponding local model updates for the next stage. The remaining local model updates are then clipped to a norm threshold and finally aggregated to update the global model. We evaluate FLShield against 4 different types of poisoning attacks on 4 different datasets across 2 domains. We define 2 baselines for comparison, Fedaverage and Fedoracle. Fedaverage is the no defense aggregation baseline, and Fedoracle is the baseline in which we assume that the server has this Oracle-like ability and can filter all the malicious model updates. Therefore, Fedoracle works as a milestone benchmark for defenses in that way. We also compare FLShield's performance against 4 state-of-the-art existing defenses. We found that both versions of FLShield consistently achieve similar performance as Fedoracle across all the poisoning attacks. For FLShield, with the star denotes the cluster-based variation, and FLShield with the cross denotes the bijective variation. For inner product manipulation attack, the performance is reported in mean accuracy, which refers to the final global model accuracy on test set. For targeted label flipping attack, the recall of the target class is reported. For backdoor attack, attack success rate denotes the percentage of backdoor triggered samples misclassifies to the target class, and it is chosen as the reported metric. We also found that both versions of FLShield consistently outperform state-of-the-art defenses. In each column, the best performing defense is one of the two versions of FLShield. We evaluated FLShield in two non-IID scenarios and found that the both versions get similar results at Fed Oracle. The attack for which the performance is reported here is the targeted level flipping attack. We designed two defense-aware attacks, FA Adaptive and FA Advanced, which employ malicious validators to disrupt the defensive process. We found that FLShield can consistently detect malicious validation reports, and the performance of FLShield remains unimpaired in the presence of this defense-aware attack. We attribute this success to the design of validation reports using LIPC scores. In the figure, it is visible that malicious validation reports are significantly different than their benign counterparts. Additionally, we launched gradient inversion attacks on representative model gradients and found that the attacks are unable to uncover any of the training samples. In conclusion, our proposed framework, FLShield, can defend against all categories of poisoning attacks, including defense-aware attacks that we designed. FLShield can do all this while incurring a small computation and communication overhead required for the validation process. In future, we plan to extend FLShield's approach to non-classifier based FL models such as regression models. Thank you everyone for listening to my talk. If you have any questions, please email me at ekabir@psu.edu.